Hi, welcome to Numerical Tactics, the show where I try to explain algorithmic concepts by coding in front of you. This is the inaugural episode, meaning I've never tried this before, so bear with me. Today I'm going to talk about the Quicksort Algorithm, which is a widely used and super useful sorting algorithm. Many different libraries and many different coding languages use a variant of Quicksort as their default sorting algorithm. In future episodes, I'm planning on covering some more advanced algorithms, but for now, let's have some fun with Quicksort. So the first thing I want to do is create a list, because Quicksort is a sorting algorithm and we're going to need something to sort. So I'm going to import the random library for Python, and then we'll create a test list by using one of the built-in functions in the random library. We'll choose between 10 numbers and make a list that's got a length of 10. So let's see if this is what we want. All right, so that looks cool. So let's take this list and put it in our file here. This is where we'll start coding up this algorithm. So the basic idea behind Quicksort is you take a random number out of the list you're trying to sort, and we'll just say 3. We'll choose the last number in the list, and we'll call that the pivot. Once we choose the pivot, we compare it to each element in the list. And once the comparison is done, the pivot will end up in the position that it would be in if the list was sorted. In addition to that, all the numbers to the left of the pivot will be less than the pivot, and all the numbers to the right of the pivot will be greater than the pivot. This operation is called partitioning. So once the partitioning operation is complete, we'll have 2 lists above and below the pivot that themselves need to be partitioned. And because we're partitioning and partitioning and partitioning, this sounds like a good candidate for recursion. So that's how we're going to do this. We're going to create a function that calls itself multiple times and goes through and sorts this list. So let's step through how the partition process works before we go any further. So 3 is the pivot. So let's compare it to the first element in the list. Is it greater than or less than the first element of the list? When we start this comparison, we actually have one more value that we need to keep track of. And we're going to call that value the divider position for the pivot element. So we'll call it the divider for short. And the divider will be the first element in the list to begin with. And once we find an element in the list that's less than the pivot, then we'll go through and swap that element with the divider, and then make the next element in the list the new divider. So 1 is less than 3, but the divider is 1, so we're basically swapping it with itself. And now we'll move the divider up to the next element, which is 4, but that one is greater than 3, so we'll just move on. 5 is also greater than 3, as is 7. 0 is not, though. 0 is less than 3. So what we're going to do now is take 0 and swap it with 4, which is our divider. So now we have 4 in this position and 0 in this position. All right. So now we're going to increment the divider. So now the divider is going to be 5. Okay. So what about 6? Is 6 less than 3? No. 2 less than 3? Yes. So we're going to switch that one with our new divider. So the 2 is going to go away and be replaced by 5. And the 2 is going to go over here. Now the new divider is 7. But if we see the next 2 elements in the list are greater than 3. And so now we're done. And the very last step of this partitioning algorithm is to take the 3, to take the pivot, and swap it with the divider at the very end. So 3 is going to go here, 7 is going to go here, and now we can see that very nicely we have 2 lists here, greater than and less than 3, and 3 is in the position that it's going to be in when the list is completely sorted, when the algorithm is finished. All right, so what all values do we have to track here then? Well, we know we have to track the pivot. That one's pretty clear. And we also have to track that divider value that we're talking about, that we're using in the swap. And then the last couple values that we need to track are where the start and stop are for each recursive call to this algorithm, right? Because the next step in the list, the next step in the algorithm is to sort this list, this sublist, and then this sublist. So we need to keep track of the lowest and the highest element that we're acting on. So with that information, we can get started on writing this algorithm, right? So we're going to have a recursive algorithm. We're going to create a recursive algorithm. So we're going to call this function Quicksort. And we need to track a couple things. We need to track the list. We need to have a few parameters. And we need to have a few parameters here. We need the list to sort, and then because each time we're calling this algorithm, it's going to be on a subset of this list, then we need to track the low index and the high index. Cool. So now that we know what our parameters are and we have the function, now we have to implement the actual algorithm itself. And we have to basically first figure out what our stopping conditions are for this recursion, right? And the stopping conditions are when the low index and the high index are the same, right? Because it's a list of just one element, because one element is sorted, and this space is bugging me. Okay. So we're going to say if the high index minus the low index is greater than 0, continue with the algorithm. Otherwise we're done. So if we're continuing with the algorithm, that means the next step is to actually do the partitioning. And it may be much clearer to put that partitioning step, because it's a discrete chunk of work, so we can put that into a separate function. So we'll call that partition, and so we'll set whatever the return value is from partition to P, and then what do we need to actually pass into partition? Well, we definitely need to know what the list is, the list to sort, and the low index and the high index, right? Now, once the partition is complete, that's going to give you 2 more lists to sort. So we're going to have to call Quicksort then 2 times on both sides of the partition. So say partition is the pivot from when we talked about how the algorithm actually works, and so if we call Quicksort with the list to sort, and then the low index will be the same low index, but the high index is going to be 1 less than the partition, the value that the partition returns, 1 less than the pivot, because we know the pivot is in the correct order, and we want to continue sorting the sublists that we know are not sorted yet. So low index and then P minus 1 for the high index. Now that sorts the lower portion of the partitioned list, and we definitely want to sort the high end as well. So we'll say list to sort, and then this is going to be on the other side of the pivot, so we're going to say P plus 1 and high index for the other sublist to sort. Now, that actually looks good to me, because if we go through this and sort, it's going to, the first time through, partition, then sort the low end, the low list, and the high list after the partition. And then it's going to do that same thing to every sublist as we recurse through. And once we get down to a single element, it's just going to say, okay, we're done. Now return. So this should work. And the next step we need to do is the bulk of the work, which is write the actual partition function. So okay. So as we called it up in Quicksort, we have to write it the same way we called it in Quicksort. So it needs a list to sort, it needs a low index, and it needs a high index. Could keep this consistent. with the other function definition. So what were the things that we needed to keep track of here? The pivot was one of them, and that divider was the other one. So the first thing we want to do is actually set that divider to the low index, because that's going to be here, right? And the pivot itself is going to be the high index here. And we don't have to select the high index to be the pivot. It could be any element, but just for consistency, we're going to always choose it to be the high index. It could be, you could choose the middle index or the low index or whatever, and switch this algorithm around to suit your needs. But being consistent is going to make things a lot clearer here. So now that we have the initial values for those two things, let's go through and actually partition this. So when we partitioned, we were comparing the pivot to every element in the list. So we'll write a for loop to go through every element in the list. And remember, that's every element in the sub list denoted by low index and high index, and that's important. So for I in the range from low index to high index, we'll go through and compare. So what we're comparing is the pivot to each individual element. So we'll say if list to sort of I is less than list to sort of the pivot, then we have to do the swap. And if I recall correctly, in Python, you can do a swap like this. So we'll say list to sort of I and list to sort of the divider. Is equal to list to sort of the divider, list to sort of I. So that's just going to swap those two elements of the list. Put divider into I and I into divider. So now that we have swapped those two elements, we need to increment divider to point to the next element up in the list. So we'll say divider, add 1 to it. All right, cool. So that's once we get through all those elements in range from low index to high index, and we've compared each one and swapped as appropriate, then we need to take that last element, which is the pivot, and swap it with wherever the divider is right now. So we'll just copy this swap and instead of I, we're going to swap with the pivot. All right, so now we've gone through and partitioned the whole list, well, the sublist that we pass into the partition function. And so the last thing to do it then is just to return that divider, which is where our pivot now resides, that divider index. All right, so now that we have our algorithm implemented in what looks like a good way, we'll go through and test it. So we'll definitely test this case that we used initially, and we'll call it test list 1. But we also would like some other test cases, and it's always good to test corner cases. So I'm going to go through and make these already in order, ascending and descending. And that may catch some strange behaviors if we have them. Okay. So now let's do some tests on our test lists. So sort test list 1, and then since these are all 10 elements long, then the low indexes and the high index should be 0 and 9 for both of them, for all three of them. And it's probably a good idea to see if they're correct. So let's print those out. Okay. So here goes nothing. And let's take a look at this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Sweet. That one's sorted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And those two lists are sorted as well. So this actually works. So now that we know that this works, let's take a look and see how fast it actually is. So Quicksort is used in all kinds of libraries, and it's a very popular sorting algorithm. The reason it's very popular is because it can sort in O n log n complexity. So on average, the worst case, well, let's actually go through and see what the worst case is. So every time a partition function is performed, every time the partition function is performed, we're going through the entire list, right? So that's n. So that's n operations, where n is the size of the list. How many times does that actually happen? Well, it happens however many times we have to partition the list. And however many times we have to partition the list is determined by what the list looks like to begin with. If the list is in descending order like this, then we're going to have to partition the list for every single element. And so if we're partitioning the list n times, that's n times n, that's n squared complexity. And so that's very poor complexity. But what if we randomized this list before we went and sorted it? Then we wouldn't have to go through and perform the partition function 10 times. We would only have to perform it log n times on average, because that's how deep the recursion tree is going to be. And so in practice, many people have gone through this many times. This is a well-researched function, and it turns out that in most situations, this sorting algorithm actually performs slightly better than most n log n complexity sorting algorithms. So that might be a little bit of a controversial statement, depending on your experiences and what you are using sorting for. But in general, this is popular for a reason, right? So, okay, so that's a wrap. Thanks for watching. If you have any requests for future algorithms for me to cover, please feel free to leave a comment, and I'll definitely consider it. If you have any sorts of suggestions for changes to the format or anything, I'd definitely appreciate to hear, because I'd like to explain these algorithms in a way that's the most useful for people. Later.